Welcome to Math 1324, Lecture 4.2, where we're looking at applications of exponential function. This should be a relatively short lecture because what we're going to do is just build on what we learned in Lecture 4.1 and do a number of different types of problems and examples. So today our brief pause is going to focus on responsibility. Your attention, please. No one is coming to save you. This life of yours is 100% your responsibility. Accept responsibility for your actions. Be accountable for your results. Take ownership of your mistakes. As we move from high school to college, we have this shift in really responsibility, although we always have some self-responsibility as we're aging and maturing. But there's a huge bridge there that once you move from high school, where a lot of the responsibility for your learning is on the teacher's part, once you get to adult learning or college learning, the responsibility shifts to you. That it is your responsibility to make sure that you're getting the knowledge you need from not only from the instructor in front of the classroom, but also from the materials, and actually taking some initiative when you aren't getting what you think you need or you're not grasping the material. So right now this is very relevant to where you are academically, but this is also really key in your future career. Everyone's going to make mistakes. You're going to make mistakes, and the key thing to handling situations when you've made a mistake in a professional environment is to, if you can, fix whatever the mistake was first, if you can do it relatively quickly. Communicate very quickly. Hopefully you've been able to fix the mistake. Communicate the mistake to key stakeholders, your boss or peers or coworkers. Take ownership of that. Take responsibility for that. Perhaps apologize. If you want to explain why, and this is where most people go, they have a long explanation. If you want to explain why a mistake occurred or what happened for you, make it short, make it brief, make it high level. Do not put in there a lot of details about your aunt in the hospital and the operation and the time, etc. I had some personal issues going on. It took me away from my work for a couple of days, and I apologize. I'm back on it. And then, so again, take responsibility, fix it if you can, communicate clearly and quickly. If you're going to explain it very briefly, 1 or 2 sentences, and then make a new commitment. And I promise I will do better moving forward. So knowing how to handle mistakes is key as well, and when you've dropped the ball. The next quote is, accepting complete responsibility for your life means that you refuse to make excuses or blame others for anything in your life that you're not happy about. If you're not happy, figure out a way to change it. And our last one is from Abraham Lincoln. You cannot escape the responsibility of tomorrow by evading it today. This is a big one for me. If you're a procrastinator, it's going to catch up with you. It'll catch up with you in your grades. It'll catch up with you in not sleeping. And these are all skills that you can learn. And in our last one, we looked at how we progress by reflection. And so looking at our mistakes is a great place to reflect on. Making mistakes or dropping the ball, not taking responsibility or not being responsible is maybe a better way of saying it, is very common for all of us. We do it in some area of our life, probably at every moment. And there's trade-offs, right? If I'm totally responsible to my job, I maybe have to let my family down, and vice versa to some degree. So thinking about what you really want, how you're going to get it, and not blaming others. Sometimes there are other outside forces, but ultimately you have to decide what to do to make the change in your own life. Okay, let's get on with our lecture. Under normal exponential growth function. Under normal condition, growth can be described by a function of the form f of t equals y sub 0 e, or Euler's constant, to the power of kt, or f of t equals y sub 0 times b raised to the power of t. F of t represents the amount present at some future time t. Y sub 0 is the amount present at time t equals 0. We call this the initial population, the initial amount. If it was a loan, it would be the total amount you borrowed. If it was an investment, it would be the total amount you put in or invested, etc. K and B are constants that depend upon the rate of growth. And so you can see in the second equation, B is the constant base. And in the first equation, K is a multiplier of T in the exponent. When K is greater than 0 or positive, we describe f of t as modeling exponential growth. And when K is less than 0 or negative, we describe f of t as modeling exponential decay. Now look at these two equations and notice that since e and k in the first equation, e raised to the power of k, are both constants, e to the power of k, e to the k is also a constant. This is like 3. If e was, we could estimate Euler's constant at being 3, for example, and k is 3, we'd have 3 to the power of 3, which would be 27. So e to the k is a constant. These are really pretty much the same equation where e to the power of k is replaced simply with the constant b. So if you know what the k is in the first equation, you can do e to the k and rewrite it as this second equation, okay? E to the power of k is a constant, and that is equivalent to b, and that's why we have these two equations here. Exponential growth function, example 1 in finance. Since the early 1970s, the amount of the total credit market, which is the debt owed by the government, companies, or individuals, as a percentage of gross domestic product, GDP, can be approximated by the exponential function f of t equals y sub 0 e to the 0.0 t, where t is time in years, and t equals 0 corresponds to the year 1970. And remember that f of t is a percent. This is comes from data from the Federal Reserve. If the amount of total credit was 155% of the gross domestic product, GDP, in 1970, find the percent in the year 2005, okay? So we have the exponential function, but we're not given the initial population, y sub 0. But notice in A, it says the amount of the total credit market, which is what f of t equals, was 155% in 1970. So this is automatically telling us this is the value for y sub 0. Because remember, t equals 0 is 1970, and we're told that amount in 1970. Okay? So we can write our function, f of t, as 155 from the data given in part A and the formula, e to the power of 0.02t. It's asking us to find the percent in 2005. Now remember, we have an index. 2005 is 35 years later after 1970, so we're going to plug in 35, not 2005. 155 e to the 0.02 times 35, easily put it in our calculator, and we get 312%. So the total credit market tripled, is triple the amount of the it's triple the amount of the gross domestic product. It's 300% of the gross domestic product, sorry. Because remember, this is a percent, so the money we owe is 3 times the money sort of that we create, or etc. So this is like saying, let's say you made $50,000 a year, you would have $150,000 in debt. Your credit debt is there. If the model remains accurate, what percent GDP will the total credit market be in the year 2015? So what will T be in 2015? Well, 1970 to 2015 is 45, right? 45 years later. So we just plug in 45, do the calculation again, and now we're almost at 400%, or 4 times. This is going in the wrong direction, guys, right? So gross domestic product is, you can kind of think of that like your income, all the things that you're creating and making money on. And your credit debt is all the things that you pay. And this is saying we're going in the wrong direction. Instead of paying down our credit is going up. Example 2 for exponential growth function is a business example. Cigarette consumption in the United States has been decreasing for some time. Based on data from the Centers for Disease Control and Prevention, the number in billions of cigarettes consumed can be approximated by the function g of x equals 436 e to the negative 0.03x, with x equals 0 corresponding to the year 2000. Find the number of cigarettes consumed in the years 2005 and 2010. Well, these are simple calculations we can put in, since we have an index, 5 for 2005 and x equals 10 for 2010, simply into our formula and calculate. But since I'm asking for 2 different values, I would suggest that you plug in this formula in your y equals function. It's the top left button. So y equals 436e raised to the power of left parenthesis negative 0.036x right parenthesis. And then you can hit the graph button, the upper right button, but use the table function, which is above the graph button, and use the blue second button to get to those tables. Then you could simply go down the x values till you got to x equals 5 to see the value for 2005, right? So we'd have 364 in the y column, because remember, g of x is our y. We could continue down that table to 10 for the value in 2010, 10 years after the year 2000, and we would see the value of 304. And remember that these are in billions, okay? So if you have multiple answers for the same formula, it's often a good idea to plug that formula in using, again, your y equals button on your calculator. Because once you've plugged it in, you can compare the original formula given in the problem to what you've entered and make sure you haven't typed it in wrong. If you try to do this calculation twice, just keying in both, plugging in a 5, then you've got to type this whole formula in and make sure you have the parentheses in the right place and you don't do anything inaccurate. Okay? What also can happen is, question B, if this model remains accurate, when will cigarette consumption fall to 250 billion? Well, in the last chapter, we did this by graphing 2 equations. We graphed the original formula, g of x equals 436 e to the negative 0.036x. That's our y sub 1. And we're trying to figure out when does that y value hit 250. So in our y sub 2, right below that, we hit y equals 250, a constant. Then we use the trace button. It's the second button on the top right from the right, and we're going to use the calc feature, which is its second function above it. So the second blue key in calc, and then go to intersection. What's going to happen is you're going to get a graph that looks like this. You've got to make sure you can see both graphs and where they intersect in your calculator window. Notice the y-axis goes from 0 to 500, and the x-axis goes from 0 to 20. You can kind of figure that out in the by the data. we're looking at, we see that we had data of 364 billion, 304 billion, and we're looking for 250 billion. So those are all our y values. So we want y to go at least from 0 to about 400. And then we're looking at years from 0, and we're already up to 2010, which is 15. I'm sorry, 2010, which is 10. So we probably want to go out at least 20 or 30 years. Okay? But here's another thing you can do. If you did use the table function to answer problem A, instead of doing the graph and finding the intersection, again, remember when you get here, when you've put those both in and you can see both graphs and you hit the intersection function, you're going to get a little dot on one graph, and at the bottom it's going to say, is this your first function? And you hit enter. Yes, it is. And that little dot should move to the other graph line shown, and it'll say, is this your second function? And you say yes. And then it'll say, do you want to guess the intersection? You just hit enter again, and it'll highlight the point there that you see, and then you see the value at the bottom. Now remember, it's 15.449. So this is in the middle of year 15. Well, middle of year 15 is 2015, probably about June, which is still in the year 2015. Okay, if you want to use your table, you would go down until the y value hit 250. Now, it's never going to hit 250 exactly, or probably very rarely, as you can see here. So when it's 15, it's going to be below 250, and when it's 16, it's going to be above. How do you know which one to pick? Well, you need to pick the one that's below the higher value. Maybe at x equals 16, it's 252. Well, that means that sometime during year 15, it hit 250 because it's going down. So you got to pay attention to these. If you're going to use the table, you got to pay attention to these, even if you use the graph, and be able to interpret what this means, especially if it was like 15.7, because a lot of students will think, oh, I'll just round that to 16. No, 15.7 means probably about October or so in the year 15, which is still in the year 2015, not in the year 2016. So some interpretation is here, and some paying attention to details as well. Let's look at example 3. This is a finance example. When money is placed in a bank account that pays compound interest, the amount in the account grows exponentially, as we shall see in chapter 5. Chapter 5 is going to be your favorite chapter because it's all about money. Suppose such an account grows from $1,000 to $1,316 in 7 years. Find a growth function of the form f of t equals y sub 0 b raised to the power of t that gives the amount in the account at the time of t years. Okay, so we have this generic formula that doesn't have any values in it. Okay, so we need to figure out, and that's what the question is, figure out the actual formula. Well, we know that y sub 0 is our initial population. So in this case, it's a population of money. What's our initial amount of money? Well, the money grows from $1,000. So our y sub 0 is 1,000. So now we have at least part of the answer, that f of t equals 1,000 b to the t. Okay. We also know that 7 years later, or when t equals 7, the amount of money in our account will be $1,316. So what we can do is we can set up this equations as being equivalent. So if f of 7 equals 1,316, this is saying that t is 7. Well, we can put the f of t function, which is 1,000 times b to the t, but t is 7. And now we can calculate what b is equal to, okay? By setting these two equations equal, plugging in 7 for t, and then using this amount that we know is going to be there in 7 years, we have an equation we can solve for. The first thing we're going to do is divide both sides by 1,000, and we get 1.36. Now, what we have to do to get rid of the 7 exponent is, take the 7th root of that, which is the same as raising both sides to the power of the reciprocal. To find what b equals, we raise both sides to the power of the reciprocal, which is 1 over 7. And you can do this in your calculator. Right above the divide button is a button that looks like a little tent, the roof of a tent or the roof of a house, and that is your exponent. So you would put 1.316, that button, the little roof, house roof, and then your exponent, you would put in parentheses, left parenthesis 1 divided by 7, right parenthesis, and hit enter. And so here we get the value of b. Now be careful, this is not our answer. They want us to show the growth function. So we just plug that back in, and our money will grow at the rate of f of t equals 1,000 times 1.04 raised to the t power. Okay. Now notice here again, you have to do this backwards. A lot of students get this wrong even if they put the 7 in there. Okay. Remember that exponents come before multiplication, so you do not multiply 1,000 times 1.04 and then raise it to whatever t equals. You do the 1.04 raised to whatever t equals and then multiply it by 1,000. This is just saying how much is in the account after 12 years. We plug in 12 and we get that amount. Okay, $1,601.03. I'm not going to do that. That's a pretty straightforward calculation. The hard part here is calculating the value of b. And a key thing here on this slide again is when you're trying to figure out how to get rid of that exponent, raise both sides to the reciprocal. If this was an 8, we would raise the right side to 1/8 power to get the value of b. Okay. Infant mortality rates in the United States are shown in the following table. And this table comes from the U.S. National Center for Health Statistics. Okay. Let t equals 0 correspond to 1920. Use the data for 1920 and 2008 to find a function of the form f of t equals y sub 0 b to the t that models these data. So we're going to use this point here. 1920 is our starting point. That's t equals 0. And then we're going to use 2008 down here. Well, if t equals 0 at 1920 and 2008, that would be 88 years later, or t equals 88. This is exactly like the problem on the previous page, just different data. So why don't you pause for a minute and see if you can figure out the function like we did in the last case. Okay, figure out what your y sub 0 is, and then set up the equation so that your y sub 0 b to the t equals the amount in 2008. Okay. Well, we know that y sub 0 equals 76.7 because that's our initial population or our initial data point. We also know that t equals 88 in 2008, so we can set these two things up as equal. So again, 76.7 is our y sub 0 times b to the t, and again in 2008, t is going to be equal to 88, and this equals 6.6. We first divide both sides by 76.7 to get b to the 88, and then raise the right side. Make sure you put that whole fraction in a parenthesis, raise it to that power with that little tent guy on your calculator above the divide key, and make sure you put the the exponent 1 over 88 parenthesis 1 divided by 88 parenthesis as well before you hit enter. Okay. Otherwise, it's going to say, if you don't put the parenthesis on the exponent, it's going to say 6.6 divided by 76.7 raised to the 1 power. Done. It's going to be the same thing. And then it's going to divide that whole number by 88 because division comes after exponents. And so it's just going to do them in the order it comes. And it's saying, well, you said raise it to the first power and then divide it by something. No, you want to divide it by this fraction. So make sure you put the exponent in parentheses as well. Okay, and this problem asked us to find the actual formula. So again, we plug that back in. This is our b, remember? We were calculating b, and so we just plug in all these values. Y sub 0, 76.7. B equals 0.97251 raised to the t. That's the end of our lecture today. Good luck on these. There's not a lot. I think there's about 10 problems in your homework. Take your time with them. Make sure you understand how to solve for b, how to plug in values, how to find when, what is the x value that reaches a certain value. And I've shown you two ways again. You can use the graph and intersection, or you can look at the table and see where it hits that value. All right, good luck with your homework and reach out if you need help.